said, we are 9 people, me, Igor from the IGB from Germany, Stefan Simis from PML and the UK, Valerie McCarthy from the DKIT Ireland, Alo Laas from the Estonian University, Kathy Waters and Paul Hanson, that you know pretty well from Carey Institute and University of Madison, Wisconsin-Madison. And we are super lucky because we have other additional trainees for the hands-on part of the workshop. There are Xiao Han, Mark Warren, and Nick Sens from PML, the Lakes team from PML, and also Silke Smith, who will join us for this part. We have this workshop divided in 5 parts. The first part is going to be delivered by Alo and Valerie. We want to highlight here the synergies between technology and satellite remote sensing. Then the 3 next parts are going to be more technical with hands-on exercises. And the last part, the part 5, is going to be in charge. Kathy Weathers and Paul Hanson are going to be in charge of the wrap-up and next steps. So this is the schedule that we have. We are going, the technical parts are going to be 15 minutes of 30 and 20 minutes of hands-on exercises. So I hope you all enjoy, and I will be super. We will all be here for you to any question or doubts. And so it's my pleasure now to give the floor to Alo and Valerie to start with the part 1 of the workshop. So Alo, it's yours.
You're on mute, Alo.
Good technical things, what always happens with the virtual meetings. So sorry about that. Super great to see you all in here. Me and Valerie are going to present you some things we are working with in nowadays. But while we are not, while our work is not really directly connected with remote sensing, we have got some help from Kersti Kangro and Krista Allikas from Tartu University in Estonia and we are using their help to have some slides with a nice remote sensing imageries for you today to present. So at first, I would like to say that we all most probably know that the in-situ monitoring deals with many things. But at the same time, you all need to know that remote sensing can be used for many different things to be able to study our water systems in nowadays. So we could use them to specify the water levels of the different water bodies, to find out their thermal conditions, to see is there any water in some areas, even to measure does the soils have enough moisture, and then see the coverage of the vegetation in different areas, some snow or ice availabilities in different areas, and also different water quality measurements or data is easy to find out through remote sensing studies nowadays. All the examples I will bring today are going to be presenting the water quality issues, because this is the main area of mine in my studies. So, simple question: how the remote sensing can help us to improve the results and understanding of conventional in situ observations. Most of us are dealing somehow with the in situ studies, collecting some data from our lakes. So how remote sensing can help us, and why we should consider to work together with the people who are dealing closely with the remote sensing studies. I will bring you an example from my own country. In here we have one really large lake which is 2,600 square meters, square kilometers in size. And this is in the border of Estonia and Russia. In the first image in here, you see that this lake is really nicely covered with monitoring points where the observations in different mounts are taking part. The bad thing is that half of those points are in Russian side. So, and the cooperation between Estonia and Russia is not so good in case of studying this lake altogether. We are lucky we can get at least 1 or 2 times per year a kind of common studies all together when we all visit those points. But at the same time, even if you see there here in the Estonian side, we have many points. Only 9 of them are used for the regular monitoring, because those 9 points are really really different from the other ones we have. So still, lake is huge. There are many points, but the data we can get is not representing the lake super nicely. So example for you in here. Let's just say that this is we have a data of chlorophyll A measurements in some mounts in some summer mounts in Estonia. So if I would now draw you a colored map how the chlorophyll A is seen in this lake, see that it changes in some parts, not super strongly. In some other parts, there is a little bit more chlorophyll, and in those areas, you see that the chlorophyll concentrations are really going in higher levels. You see that everybody would expect that there are really different patterns, a little, at least some parts of the lakes. This large area should be much more different than others. Here, if we are going to use the help from remote sensing observations and calibrate the remote sensing products with the in situ data, we see how different are actually the chlorophyll patterns in this lake. So there are, just using those some points in here, we have in situ measurements, and getting other points from Earth observation data, we see that there are many different areas which patterns of chlorophyll A are much different than it was in here, assuming just the in situ monitoring. So clear evidence that remote sensing can easily help in situ part. Another part, what we are interested is that remote sensing people actually need our help as well, because their products cannot be as good as they would hope without in situ data. To prove that, I will just show you some images in here. You will hear more about this in the first image in here. This is a level 1 image. You will get this information later on, what is level 1, level 2, and level 3. But this is the first image they can get from the remote sensing databases in case of this lake. And if they just do a simple atmospheric corrections with this model in here, which is described in here, that would be the image what they would get. Just looking this data sets, we see that in those areas where the chlorophyll A concentration should be high, there is really underestimation. So we would expect much higher chlorophyll concentrations in here in those parts of the lakes. So with this, we can see that the product itself is not so good yet. So what they should do is that if they are able, they can use in situ data and calibrate their algorithms with this and to get much better picture. So you see the same picture now, and again, like the earlier results, we're not having any in situ measurements, and now everything in here is really improved with the in situ observations. The good thing in case of having remote sensing for our in situ studies is that nowadays remote sensing really enables us to conduct even time series analysis, which earlier was, let's say, that the coverage and the images were not in so good quality level, and there was many things which were disturbing, like there was many clouds on that days when the satellites were passing your lake, you could not get a nice image. Just showing you examples from the same lakes. Already 2007, you see that, that after every like 3 or 5 or sometimes after every 10 days, you will get a super nice image of this lake. And having such frequent data, we are already able to compare remote sensing observations, the ground observations. For example, in here in those graphs with the wind speed and air temperature. Same in this other months in here. And you see that, that normally when we will go only once a month to the lake to collect the in situ data, and remote sensing helps us many images between those in situ measurement times. The other cool thing with remote sensing is that we can really go back from the history now as well. That we can make, like in here you see yearly average chlorophyll maps in the vegetation period, so we can see how the years are differing from each other. Another very important thing is that most of us in here are somehow connected with the GLEON, so we are somehow connected with the in situ observations. So for all of us, it is super important to get as good data and to collect as good data as we can. But our measurements are really valuable for the remote sensing studies as well. So those people who are able now to collect nice images from space about our lakes really need to calibrate those images. And in here we see the high importance of high frequency studies in our lakes. So if you are able to install a buoy system on your studied lake, or if it's there already, it is extremely important to have really accurate and good data which we could share with them as well. So those networks, those in situ networks, really need to improve this data sharing with them as well. So it would be good to have a kind of a common databases, or at least metadatabases to present where this data can be collected and where this data can be asked for them to use as well. And there are many global products available which are openly available for many of us to use, and you will see some of those products today from the other part of the workshop. But it is extremely important to have also regional products, and that those could be adopted in your lakes, which gives you a much clearer and much closer to the truth pictures of your lake studied with both in situ and through the remote sensing observations. So that was our short introduction for you to have an appetizer before the real thing starts today. Thanks a lot.
Thanks, Alo. So now is my turn. I will share my screen. We're going to start with the technical part, let's say, to the real remote sensing part. So this is, we are going to start with part 2, which I'm going to deliver. It would be mostly the basics of aquatic remote sensing, how basically remote sensing works, and then we are going to jump into a hands-on exercise that I will explain afterwards. Okay, I forgot to present myself. I work in 3Data, that it is a spin-off company from the university. My background, really, my PhD was in limnology, so my background is, I have quite a strong background in limnology, mostly shallow lake, coastal lagoons, and all this kind of environments. And from several years up until now, I'm working mostly with remote sensing. Is nowadays my main field of research and work, and with this let's say, type of knowledge, I'm trying to deliver routine monitoring product mostly for drinking water reservoirs. So let's start really with the important part. how remote sensing works. Okay. First, what is remote sensing for us? Remote sensing means for us is the science of acquiring information about the Earth's surface without actually being in contact with it. So we do this by sensing and recording the reflected or emitted energy, and afterwards we process, analyze, and apply that information. This process needs, in our case, that we are talking about passive remote sensing. This means that the sensor is not delivering any energy or source of energy. It just registers the energy that comes to it. So this is what passive remote sensing means. And for us, the energy source would be the sun. So this energy source will let's say, deliver electromagnetic radiation that is going through the atmosphere, then it's hitting the target, that is what we want to study, either vegetation, in our case, water, or any land cover. And then there's this interaction, and then the signal that comes from the target arrives to the sensor, going again through the atmosphere, and there it is recorded. It's not in contact with the target, as you can see, and then this information comes direct to the station where there is the data retrieval, storage, and followed by a distribution of the data. So afterwards, with this information, the experts, what are going to do is to interpret, analyze, and use it for different applications. In this case, it is a map of chlorophyll in a Spanish reservoir. What I am trying to this small example. So this is the process, the entire process, and now we are going to go little by little from the very beginning until the very end. So first, what I want to highlight in this slide is how everything works. So from the sun, the electromagnetic radiation is instant into the target. It goes through the atmosphere, and there are absorption and reflection and scattering in the atmosphere. And then we have the reflected electromagnetic radiation and the emitted radiation from the vegetation, and then it is recorded in the sensor. And how it is recorded? It is recorded in what we call digital numbers. That it is what the detectors that are in the sensor that go on board satellites or drones or planes or whatever device is recorded. The digital numbers are proportional to the radiance at the sensor, to the radiance that the sensor receives. So this is how the data is stored in an image, in rows and columns with digital numbers. The digital numbers, let's say, measure the brightness value, and they typically go from 0 to 255, and they have an associated grayscale from black, that it is 0, to 225, that it is completely white. So this is what you can see when you open an image and you see, let's say, one band. You see a grayscale. Your eyes see different levels of gray, and the levels go typically, as I said, from 0 to 255, but they can go to 0 to 511 or to 0 to 1023 in binary scales, to 8, to 9, or to 10. And your computer, what it sees, your computer is the digital number that describes this grayscale. So that is how the data is stored in an image. Then this data is for each and every one of the bands that each sensor has. And now we are going to jump into what it is a band, and let's try to explain this, talking about the sensors. Okay, the different sensors, we can explain that through the data resolution. the different types of resolutions that we have in a sensor. We can talk about temporal resolution, spatial resolution, or spectral resolution. With temporal resolution, we want to refer to the frequency of flyovers by the sensor over a location in the Earth's surface. With the spatial resolution, it refers to the ground size of an image pixel, which may be as small as 1 meter for airborne system, or even less, even centimeters if the sensor is on board a drone or something that flies lower, or even more than 1,000 meters for satellite systems. And then finally, the spectral resolution. The spectral resolution refers to the number, spacing, and width of the different wavelength bands recorded. It can be even a broad band covering the visible spectrum to even several hundred bands, each of them few nanometers wide. We can describe the spectral resolution by the sampling interval, which is the spectral distance between the two consecutive peaks, and the bandwidth or bandpass, which is the width of the spectral channel response to a monochromatic light. So with this, we can differentiate multispectral versus hyperspectral sensors. We can talk about monochromatic, which refers to a sensor with one very narrow wavelength band. It can be laser, for example, wavelength. We can talk about panchromatic, which refers to one very broad wavelength band. Usually it's on the visible range. And you can see this in a black and white photograph. We can talk about multispectral sensors that have several wavelength bands, each typically more or less 10 to 20 nanometers wide, and last hyperspectral sensor. Those have 3 or more bands, narrower, and typically they can have more than 100 bands, each of them less than 5 nanometers wide. As you can see in the image, an RGB, that it is kind of what we can see as a normal camera, photographic camera. It has just 3 bands in blue, green, and red. A multispectral has much more bands. And then the comparison with the hyperspectral band, that it has more than 100 bands, and it allows us to detect almost the whole spectrum. So it gave us a lot of information, much more information. Each and every one of them gives us much more information. So these sensors can be on board of different devices, let's say. They can be normal planes, but mostly we are going to talk about satellites. Here I want to highlight just the most important missions for nowadays, and some of them in the past. The ones that were, even though they were not meant, most of them for aquatic studies, they have been widely used for that. So the most important ones, I would say, from talking about the European Space Agency, then we are going to talk about NASA, but first we are going to explore European Space Agency missions. Starting from the past, the MERIS sensor on board Envisat, it was a sensor that was used for observation of oceans, atmosphere, and land. I here put the spatial resolution and the temporal resolution just for you to have more a glimpse of what they can do. MERIS is not operational anymore. It had 300 meters of spatial resolution and a temporal resolution of 3 days. One of the most used right now is Sentinel-2, Sentinel-2A and B, the 2 satellites. They both carried a multispectral sensor, the MSI, that has different bands with different spatial resolution of 10, 20, and 60 meters. They have an overpass of 5 days with the combination of the 2 satellites. Then the Sentinel-3, that it is kind of the one that comes after MERIS. This is also for the observation of oceans and atmosphere, and it carries the OLG sensor, that it is another multispectral sensor with 300 meters of spatial resolution, and that comes with at 2 days overpass. And looking into the future, the next mission that could be really important for the aquatic system would be the Copernicus Hyperspectral Imaging Mission for the Environment. It is called CHIME, and it is not operational, but it's going to be in the following, maybe next year. And it has a resolution of 20-30 meters, and it will overpass each and every 12.5 days. The NASA missions, it's important, super important really to highlight the Landsat missions, all the past Landsat missions that gave a lot of data for aquatic systems. Nowadays, the one that we use most is Landsat 8 with the multispectral sensor, OLI, with 30 meters of spatial resolution and 16 days overpass. Also, MODIS is very important for aquatic system. It has different bands. It's also multispectral. It has different bands with 250, 500, and 1,000 meters of spatial resolution, with an overpass of 1 to 2 days. And also looking into the future, the PACE, the hyperspectral PACE mission, that if I remember correctly, we have also a workshop a couple of years ago, or 1 year ago, about this mission delivered by NASA. So now that we know how passive remote sensing works, what is a wavelength and what is a multispectral sensor and what are the bands, let's jump into spectral signatures and the magnitudes we are talking about. It is true that the sensor registers the energy that comes to it, but the important thing is not only what comes, but what comes in relation of what enters into the target, what arrives into the target and what leaves the target. And that is a ratio that is called reflectance, and there's the main magnitude we measure with remote sensing. Is the ratio between the downwelling irradiance with respect to the upwelling irradiance. Here we can see the signal recorded by a sensor in reflectance of different targets. We can see grass, we can see asphalt, we can see sandy, all of them are here. And now we are going to cry all together because here is the water. The water and mostly the deep water is a dark object, a dark target. We are going to have a very low reflectance, which means that everything that interferes, and you will see afterwards that atmosphere is one of the things that interferes most with the signal detected by a sensor, is going to put problems for us to detect really this signal because it's super low. So this is a spectral signature, and this is how it works in water, that it is pretty different as the functioning of everything in land. So going backwards a little bit, we have our sun with electromagnetic radiation entering into the water, and what happens? Some of this electromagnetic radiation is reflected from the atmosphere, is absorbed and reflected. So we have some upwelling radiance from the atmosphere. Some of the electromagnetic radiation goes into the water surface and then gets reflected. So it's the reflected radiance. Some of the electromagnetic radiation goes into the water, and there absorption and scattering processes take place. We are going to see this afterwards. And then some part of the electromagnetic radiation that comes in goes out as water-leaving radiance that is really what we want to know in aquatic remote sensing. So that's why we have not reflectance as our main magnitude, but remote sensing reflectance. That it is the ratio between downwelling irradiance and the water leaving irradiance. And it is measured in per stereo radian. That is the unit. So we have to remove all this and know all of this to achieve the water level radiant, that it is what we want to know. And here we are going just to see the processes that goes through that occurs in a lake or in a water body very briefly. So the electromagnetic, the incident solar radiance arrives to into the water body, and mostly phytoplankton, dissolved organics, and particulate matter are going to be the main, let's say, substances that are going to change the electromagnetic radiation that is going to leave afterwards. And how? With processes of absorption and scattering. Most backwards scattering, that it's the one that is going out, let's say, and forward scattering. Phytoplankton, it's turning the color of the water into green. Dissolved organics, we can think about a yellowish color, and particulate matter, we can think about a more brownish color, because at the end, with optical remote sensing, what we are doing is measuring the color of the water. So, and we wanted to highlight in here that the amount of energy that it is entering it's much higher in intensity than the one that it is afterwards leaving. And both of them are going through the atmosphere, go down and up. And this is something that we have to remove afterwards to interpret the results, as Igor will explain to you in the next part. So aquatic remote sensing is mostly based in the study of the optical properties of water constituents. And we can distinguish two different types of optical properties. The inherent optical properties are, okay, we already know the remote sensing reflectance, the downwelling irradiance, and the water leaving irradiance are in the right part of this slide. Those are called apparent optical properties, and they depend on the light field. And then the others are the inherent optical properties that are inherent from the and characteristic of the water body and the characteristic of this water body. They do not change with the light field. And they are mostly related to absorption. They are absorption coefficients, and mostly to backscattering. Both of them are related. The IOPs, the inherent optical properties, link reflectance that is derived from the measurement of the optical sensor with the concentration of water constituents, and how through this formula that relates the backscattering coefficients and the absorption coefficients to the color of water, the remote sensing reflectance. The absorption coefficients are accumulative, and they are we are going to study mostly the absorption coefficient of phytoplankton, non-algal particles, and colored dissolved organic matter and water, and the scattering coefficient, the backscattering, the forward scattering. The backscattering is going to be the most important, and all these coefficients are measured in per meter. So now that we know what is remote sensing reflectance, what is a spectral signature of a water body, and what does it mean, how we record this energy and then afterwards interpret it, I just want to show you how a signature, a spectral signature can change depending on the concentration, for example, with the state of the water. Here we can see the concentration of chlorophyll, total suspended solids, and the Secchi depth. We are going to go from, let's say, oligotrophic system to a most eutrophic ones. So we start with chlorophyll, low chlorophyll, low TSS, and low and high SECI depth. And as the water is becoming more eutrophic, the spectral signatures start to change until this last one that we have here, a lot of chlorophyll, a lot of solids, and a very low SECI depth. So these features in the spectral signatures are the one that we are going to use to relate the energy register with the optical properties or with the optical constituents in water. This is another example of different types of water with different turbidities and contents of chlorophyll. So you can see here the features that I talked before. We can roughly say that here in the blue, the absorption is done by its main because of CDON. This peak in the green part could be due to solids and chlorophyll. Here we have this absorption feature that in 620 that it is because of the phycocyanin that, as you all know, is one of the pigments that the cyanobacteria have. This absorption feature in 665, it's because of chlorophyll, and in the near infrared, we have a feature that it is made by the total suspended solids in the water. So different water colors and water turbidities, what are giving us is different spectra, different signatures. So this is the end of the theoretical part. And now I would like to jump into the first snap demonstration, the first hands-on exercise. It's going to be pretty basic, just open, visualize, and explore satellite imagery. We are going to open and visualize level 1 images from NSI and from OLGI. We are going to see differences in spatial resolution and spectral resolution between both of them. We are going to see difference in the spectrum, now that we know what it is a spectral signature, difference between a single band and an RGB image. We can see the pixel information, and then we are going to jump into the subset and resampling that are two super simple procedures that are going to be really useful for the next exercises. So I will now jump into the snap. Sorry. And first, the first thing, what we are going to do, I'm going to do first the demonstration, and then we are going to split up in breakouts, and then we're going to do everything step by step. So first, we can open, we are going to open level 1 images from NSI to the XML file, hopefully. Yeah, something that we should know is that almost always things take a little bit of time. So you can see here your image in the Product Explorer. You can open it and see the metadata of the image. You can see that it's a level 1 image. This is something, this information is going to come to you afterwards, what it's a level 1 image. But what I can say right now, it is not atmospherically corrected. Here we have the bands. We can open one band, whatever is, for example. And as you can see, as we explained it before, everything is in a grayscale. This is only one band. So this is the information that we are going to have. And then we are going to compare this with an RGB. This is super simple. You click here and right click, open RGB image window, and
Carmen, we have a question. It's from Kate Reynolds. Says, can you show which file you clicked on again?
Show them?
Which file you clicked on again?
Is the MSI, but we are going to help them in the breakouts, so no worries. It's the level 1, the first one, the MSI image. So we open the one that it is here by default. And now we have an RGB image. It's more or less what your eyes would see, because we in our eyes, we have more or less an RGB camera, not exactly, but more or less. So this is the difference between one band and the composite of 3 bands in red, green, and blue. And we can also work with different band combinations. We can also make what we call it natural colors, but we can also work with a false color, and you can do it on your own, but there are some in here that are kind of by default. You click again, open RGB, but instead of opening an RGB, you can open directly a false color infrared, that it is really for seeing the health of the vegetation, but you can see that different band combination can give you different information. So this is for measuring the health of the vegetation, but it's good to see how different bands can give you different information. So coming back to the, if I can move this. Okay. Coming back to here to the RGB, you have all of them here in this part. Coming to the RGB image, I would like to show you a spectrum of water, a spectrum of vegetation, and a spectrum of a different kind of thing. So we can go to the spectrum view. It's collecting the information. It's thinking. Sorry, it's thinking. Yeah, this happens. This kind of things can happen. Okay, we can. I'm sorry. Okay, what I want to show you here is a different spectra from different targets: water, vegetation, and different and land in here. But it is not working. Now. No. It was working before, but not now. Oh, okay. I will remove the pins and try a different thing. Why? It was working nicely before.
Yeah, Carmen, it's just still opening those 12 bands, so it's a large image.
Yeah, it's that.
If
But
we,
before it was working.
If we look at the
super
Ulti image,
nicely.
it will be a lot quicker.
Yeah.
There's a button in the spectrum view you need to press to show the spectra of the pins.
No. It is not that. It is that it is not working right now. You look, it got like stuck. Sorry. If I restart everything again, it's going to be worse, I would say. Or maybe it's the thing that I should do. Sorry. Okay. It can be wrong, always can be wrong. I'm sorry, I cannot do anything. It does. It even does not want to close the snap.
If you want,
Okay,
I
the
can
next
share
thing-
my version. I have it on screen now.
Oh. Yeah, but yeah, try, and I start with that. I would like to open the OG and to show the spectra of the three different targets. But why? Come on.
Carmen, stop sharing your screen and let Stefan share the screen, and you will just say what Stefan should do.
Yeah.
So the
Oh,
difference is
Steph.
that I zoomed in on a part of the image, which makes it a lot quicker to load the underlying data. So Carmen, I'm just over a part of the main lagoon now in the spectrum view. Can you see this? Sorry.
No, I
I've done
cannot
something
see
wrong.
it.
I'm sorry. Let me try again.
It worked perfectly.
So- Seems to be rather heavy on a small laptop.
Yeah, I also don't see anything on the screen.
No.
Let me try once more. I think it took a while to load. How's this?
Yeah,
Better.
that works. Yeah,
Okay.
there you go. Great.
So this is a water pixel.
Yeah, I wanted to show the water pixel and vegetation pixel and
So we can
another
move,
type of land, just for them to see
move towards
how this-
land, and it looks very different.
That's it.
Anything else?
Just that I think is no. I'm going to, and then the idea was to have the three pins because it was super nice to see the three spectral together, but no worries about that. We can do it afterwards. Yeah. And then open the Sentinel-3, the OG image with the
Sorry, now I was doing the 3 pins, and every mouse click takes a while.
I still cannot even close my
Oh, there you go. Now you can see 3 pins together.
Okay, to the great.
And then I will close this view to free up a bit of memory.
Yeah,
Open
and open the OG level 1.
Alt-G. Do you want me to make an RGB image first?
Yeah, please.
Okay. Then it's your fault if it takes a long time.
Just to show, yeah, that one. Just to show.
Oh, could not be created. Oh, it was not happy with this. Sorry. Maybe we skip the RGB image.
But my snap was working perfectly, and I did everything several times before.
All right. I've done something wrong with opening this image. Sorry, I can't do that right now. But maybe this is a good time to try for ourselves so that we can also share what others cannot see.
Igor, can you open the image or not? My snap is saying that. No.
Here is the Sentinel-3 image, in grayscale, and we can see it's much larger than the Sentinel-2. So where's the area of the Sentinel-2 be Well, let's create an RGB first.
Yeah, because I've done this super difficult. Here we wanted to show you if you can find the same image, the same part of the image, the same, let's say, water body, or the same system. This is a huge image, but if you go to the right corner, the right side of the image, you can find there, yeah. There you have. So that is the difference between the spatial resolution between MSI, and the bands go to from 10 meters to 60 meters spatial resolution, to OG that it is 300 meters of spatial resolution. And the spectral resolution is also different because OG has much more bands, as you can see also in the product explorer in here. And the idea was to crop this image to make a subset of the OG image just with your region of interest. A super simple feature. You go to raster, subset, and just use this and say, okay, you can crop it you can crop the bands, you can put different coordinates or whatever you want to make the subset, but it is easy for this just to use the window that you have there. So click OK, and the subset is almost an immediate procedure. It opens in a snap, and you have there the subset, that it is just the same, but only with this part of the image. And we wanted also to show you how to do a resampling of the MSI image, because this is going to be very useful for the next exercise, because Igor is going to run the C2R processor, and it needs to have all the bands in the same spatial resolution. So it's as simple as select your image in the Product Explorer, go to Geometric and Resampling, and make the resampling in the processing parameters. Just change it to 20, and you will have all the bands in the same spatial resolution. This will not give you more information. It's just changing the resolution. You go run, and it is almost immediate in my laptop when it wants to work. I don't know, Igor, how is in yours? And you now have a resampled image with all the bands in the same spatial resolution of 20 meters each pixel. And this image, we are going to use it for the atmospheric correction afterwards with Igor. I'm super sorry that the snap didn't work in my laptop. It's still collapsed, and I should initiate or something, but I can't because I will lose it. So maybe trainers, what we should do now is to jump into breakouts and just show the people how to do the things. I have the instructions for this exercise. Should I will copy them into the chat, so for all of you to have them.
And then in each breakout room, there will be someone there to help you guys on running the snap. So then you can go.
I'm creating the breakout rooms now, so I will assign you soon to the breakout rooms.
Yeah, we will do all this together.
They're all assigned, so we can just, I've assigned everybody to a room. So I can start the rooms now. It's 20 minutes for each breakout room. Okay.
Okay, you already did it, Valerie?
Yeah.
Okay, great, cool, thank you.
So we have one for each, isn't it?
Yes, there's one trainer for each room. There's 7 rooms in total.
Super good, thanks.
Okay. So we have this short break here, and now we go to part 3, atmospheric correction and algorithms and optical water types. I will try to go through this theory part quite quickly, so we have more time on the hands-on, which is, I think it's the most interesting part. So, right, okay. So here we have, more or less, we were talking about different levels of satellite data. So we have level 0 when it's only digital numbers, as Carmen showed, when the satellite, the detectors of the sensors capture light and convert it to numbers. And then we have level 1, and then level 1 can be different levels. So we can have a radiometric correction, we can have a geometric correction, we can have orthorectification. So we are using the data level 1C, so it's the best level 1 we have. And then the next step is going for level 2. So how can we transform level 1 to level 2? And one of the level 2 part is we need to have atmospheric correction. So why we need to have it again? So this is more or less what Carmen mentioned before. So in the atmosphere, we have particles in the atmosphere that can reflect the light straight to the sensor without even touching the water or the target that we have. And then we can have lights that only reflects all the way to the sensor just by the surface. But what we are interested in is what it goes inside the water column, interacts with the water and goes back. And that's why we need to remove all others in order to just have the green one, that is the one that we are interested. So that's why we need to do these atmospheric corrections, to remove all these optical processes that are happening in the atmosphere or even in the surface of the water. So here on the top image is the image before atmospheric correction and one after atmospheric correction. So this was in a clear sky day, so not so much difference, but we can see here on this a little bit of haze on the left. Not sure if you can see it well in your screen, but there's a little bit of haze, and just the haze here is a little bit less. So although we cannot visibly notice a difference in this case, in the spectra there will be a lot of difference. So how can we do this? So in the 80s, there's this dark object subtraction methodology, which was consists mostly in finding the darkest pixel in the image and consider that everything is noise. So we remove this value of this band and remove everything is noise. But usually the darkest pixel is over water. So for water, it's not so good. Nowadays, we have other types of methodologies where we can go on coupling atmospheric and water content based on some physics and some artificial intelligence assisted methods that are mostly used, and they are getting more focus on inland waters. So there is also this difference. There is atmospheric correction for land, atmospheric correction for oceans, and atmospheric correction for inland waters that are all different because they all consider a little bit different. So for water, we have this extra surface of the water, sun glint. And for inland waters, we can also add adjacent effects from the surrounding land of the lakes, for example. And how do we know if the atmospheric correction is good or not, or is right or not? For this, we need in situ remote sensing reflectance that we collect via spectroradiometers. So this is a very vital data to know if the data of the correction is really working well or not. So here's an example to see if the data, the atmospheric corrections are working well. So on the lines here is the in situ remote sensing reflectance data, and at the points are the remote sensing reflectance by acolyte, C2 or CC, and C2X. So acolyte, those are all different methods or atmospheric correction methods. And we can see, for example, acolyte, it does well for the, especially in the visible range, but then in the near infrared, it's not doing a good job. This is especially because they use a dark spectrum for correction. C2RCC and C2X are getting better results in the near infrared, not so well here on the green. So this is a way where we can evaluate, and this varies from scene to scene. So C2RCC was better for this scene, but for your region or for another place, could be a different algorithm that will give you a better result. And then level 2, then we have atmospheric correction data. So we have optical properties on level 2. And why it's important to have optical properties? Because from optical properties is mostly what we want to do in terms of limnology. So remote sensing, we can have mainly two types of algorithms, the forward algorithms and the inverse algorithms. The forward ones goes from water quality, so pigments, concentration of phytoplankton pigments, organic matter, dissolved or total suspended solids or non-algae particles. So we go from this concentration, and then from this concentration, we create this inherent optical properties, so properties of absorption that we measure in the spectrophotometer, for example. And from this, we can get the reflectance that we'll see in the satellite. But for limnologists, we are interested in the inverse. So we go from reflectance that satellites get properties of absorptions, and then get the concentration of pigments. So and there's two ways we can do it. We can follow this path, getting the optical properties and then the concentrations, or we can go from this other path here that is going from reflectance straight to the concentrations, which are known as empirical and semi-empirical algorithms. So this one, we go from reflectance to the concentrations. When semi-analytical and quasi-analytical goes through all these steps here. But then waters are different. So as Carmen showed before, different colors of the water, different waters, different lakes have different colors, and they are different. So a classical approach is classifying waters in two types. One type is water there's mostly the ocean, where we only have phytoplankton in it. So it's optically simple because everything that's going to interact in the water is phytoplankton. The turbidity will be related or covariant with the phytoplankton cells, and everything is going to work as in relation to phytoplankton. So organic matter comes from the phytoplankton, so everything covariates with phytoplankton. This is an example of case 1 waters. The case 2 waters is when it's optically complex. So mostly a lot of fresh waters are optically complex because we don't only have phytoplankton in it, but we also have suspended solids. We also have colors of organic matter, and sometimes they do not covariate with each other. Sometimes we can have more phytoplankton than organic matter. Sometimes we can have more organic matter than phytoplankton, and then we can create different combinations. And because of creating these different combinations is where we can see different spectra, reflectance spectra. So nowadays, a lot of people are trying to classify on how many different water types we have, and how many different lakes in a lake, how many waters we have. For example, in the entrance of the lake coming with a lot of sediment, and then in the middle of the lake, there's not so much. So there we can already see there's two different types of water. And then we can create this water typology. So it's much more than two. It's not only case 1 and case 2. We can have much more numbers of optical water types. And why do we need to know what is the optical water types? Mostly because since the waters are so different, when we use this type of remote sensing algorithms, they do not work well when we apply it for a different water type. So the idea is that for each water type, we will have an algorithm that performs better or performs the best. The performance is the best. And then if we can classify water types first, and then we can apply the algorithm first. One example is a paper from Claire Neal on remote sensing of environment. And here they tested a lot of models and for 13 different water types. And we can see that in the end, we can have near infrared red base algorithms, semi-analytical algorithms, and blue-green algorithms. And here we can see different types of the water types, 13 different water types, and see that for each water type, there is a type of algorithm or based on different principles. So blue-green here, there is this triangle. It's only on 13 that is here when concentrations of chlorophyll are very low. So when we have oligotrophic waters is where blue-green ratio will perform better, or algorithms using blue-green ratio will perform better. And then semi-analytical is the other triangle here is 7, 6, 7, and 8, and 10. They're mostly here, so on the high end. So mostly for very eutrophic waters, while near infrared and red are mostly in the middle here. So this is also a way where we can try to figure out, well, okay, so depending on the type of water or eutrophic classification of the water, we need to use a different set of algorithm to retrieve chlorophyll concentration. And then for the demonstration now, we will use the two images that we classified and subset in the previous exercise, and then we will apply the C2RCC, which is already on Snap. And then the main task could be, okay, let's open the spectrum view and see what's the difference between the corrected and non-corrected reflectance or radiance. So now I will share my Snap. Okay. Let me close most of this first. So let's start with the Sentinel-2. So for the ones that were not here during the break, we were just saying, well, first what you need to do was the resampling of Sentinel-2. So Sentinel-2 resample here, and we need to do that because Sentinel-2 has, each band has a different spatial resolution. So some bands we have 10, 20, and 60 meters, and we do the resampling so all the bands have the same size. So from this band here, what we do, so we already have this the sample product. We go from optical, thematic, water processing, C2RCC processors, and then we choose the Sentinel-2 MSI. And then here, since we have a lot of products open, just make sure that you are selecting the one that is the resample. Then you change here where you want to save. And then and then you can, I cannot move it here. The zoom, okay, now I can do it. Processing parameters. So the first, we will use the default, but just to let you know, you can change the pixel. So here in the valid pixel expression, here it's going to remove the land and only keeps the water. So you can use a different value if you want. So you can create a NZWI, for example, to extract the pixels of water. But here is it's going to create a mask. You can change your salinity, your temperature, but let's just keep it as default here. And here you can, this is based on neural networks. So you can choose your neural network that you want to use. So C2RCC is mostly used for coastal water. C2XNet is on extreme cases. And C2X complex is a new one that they installed in this new version of Snap. And it's a more complex for, especially for inland waters. This is the one that you should look for to use. So you can choose the neural network that you want to use, and then you can apply run. Another thing, if you want to have your reflectance in remote sensing reflectance, you can click here. Otherwise, it's going to compute as undimensional water leaving reflectance. But if you want remote sensing reflectance, you can also click here, and then it's going to compute as remote sensing reflectance, and you run it. In this case, I already have it, so I can open here. So when you run it, then, maybe I don't have it here yet. Here. So when you run it, then you click here, and then you see that bands will be different. So now you have different things that they process for you. So they will process IOPs. They will process some concentrations. So you can already see chlorophyll and total suspended matter concentrations. This is all based on their neural network. And then you also have remote sensing reflectance here, TOA reflectance, top of atmosphere reflectance, and what you want to do. So I want to open a band 6 from the remote sensing reflectance here. And then I want to, let's create some pings over the water. So I'll create one here on the lake, one here in the sea. And then we can go to the spectrum view and see it here. So on the filter, we can change and say, I just want to see remote sensing reflectance and TOA reflectance, top of atmosphere reflectance. And then we can see, so this one here is before the atmospheric correction, and this is the atmospheric corrected. So we can see there is a lot of differences between this atmospheric corrected signal and the top of atmosphere signal, the non-corrected signal. Okay, and then the same for Sentinel-3. So for the Sentinel-3, we will use the subset that we created in the previous one. And then we can go again on optical, water processing, C2RCC, and then we choose ALCHI, which is Sentinel-3. The ALCHI is a sensor on Sentinel-3 satellite. And then again, is the same, you processing parameters. Let's just keep it how it is. And for the Sentinel-3, you don't have the option of selecting your neural network. So you need to stay with C2RCC. And then you just click run. And then it's gonna create also the image, atmospheric corrected image for the Sentinel-3 image. And then you can also do the same, placing pings and check how was before and after atmospheric correction. So this process will take more or less 1 minute to run. And now I will stop sharing and then we can go to the breakout and work on this. So
again, and sticking with us. What I will do is I will go through some of the options you have once you have your atmospherically corrected image. But I'm actually going to approach this from the angle of what you need to sort of know about your water body to make an informed decision about what you do next. So this comes down to algorithms. And algorithms are mathematical formulations that help you put one form of data in and then predict something on the other side. It's not the same as a model. It's not a state of the environment. It's basically a mathematical expression. I've put 3 on the screen here, and I've divided them with 2 on the left, which we will have examples of in the level 2 data that you have received, which are empirical algorithms. And then there's 1 on the right, which is an example of a semi-analytical algorithm. A main difference between them is when you start with an empirical algorithm, you decide which of my wavebands are likely going to have some correlation to what I'm interested in. For example, the concentration of the pigment chlorophyll A. And then you play with your bands and you say, let's try a power fit to my bands, or let's try a band ratio and see how I can create a correlation between this combination of bands and make a linear response to the substance I'm interested in. And that's it. When you go to the more analytical form of algorithms, you follow the inversion of reflectance, which Igor talked about. And you can see that they are a little bit more complicated. So for example, this starts with a combination of bands and known inherent optical properties, in this case of water in the near infrared, to retrieve the backscattering coefficient. And then it plugs the backscattering coefficient with a tuning factor into a model which uses a band ratio of 2 other bands, which follow the red absorption expression of the chlorophyll pigment. And then there's another factor that helps you translate the absorption that you've now extracted into a concentration of the pigment. So there's quite a lot going on there. Whereas this algorithm does a lot of the same things. It looks at the same band ratio, but then it basically says, I'll choose 3 tuning factors until this makes sense. And one doesn't necessarily give you a better or worse chlorophyll result than the other. What you need to know is for the region, for the lake, or for the lakes that you're interested in, or for seawater for that matter, how well your algorithm translates between the water bodies that you're interested in and whether the response is truly linear. And this means that usually you need to go into the field and take some samples. What we've done over the last decades is compare a lot of these algorithms every time there is a new satellite sensor and see how they perform. So this is actually work that Shahan has recently completed. So if you were in her breakout room, congratulations, you have an expert among you. We're comparing actually 4 of these algorithms. The first 3 are the ones that I showed on the previous slide. What you can see is that across different water bodies, they don't all perform equally. Igor already showed you this summary slide where some of these algorithms are combined to give a more linear response over the whole range by applying certain algorithms to certain optical water types. So that's a good way to go to a more global approach. But this is based on comparing in situ data to in situ data. So it takes reflectance measured in the field and compares it to concentration measurements, also taken from water samples collected in the field. If we go a step further and we say, okay, we now have our atmospherically collected reflectances, we can do the same. And you can see that actually we've managed to conserve the linearity quite nicely. But there is a little bit wider scatter and we see some issues occurring, for example, in the lower concentration range. So something isn't quite right there yet. And it might be atmospheric correction that shows some systematic bias, or it might be that one of these algorithms is not as sensitive as we thought. We don't really know. One further thing I'll say about this is that when you switch to another satellite sensor, this whole procedure needs to be redone if you follow this. Okay, so what do we need to do in the field to characterize our water bodies? There are many sources of uncertainty, from the sensor to anything which you do with data afterwards. The sensor itself can drift over time as well. Let's not forget that. If we want to know whether the atmospheric correction is still valid, we need to measure the color of the water itself, rather than go directly to, say, a chlorophyll concentration or a suspended matter measurement. So that means that we have to characterize the light fields. Similarly, if we want to ultimately know if we can reliably detect the concentration of a pigment, then we'll have to take those measurements in the water column as well, from water samples or directly with our instruments. So I've just listed, and I will not talk through them all. I've listed some of the methodologies in gray that you will often encounter doing these measurements, and sort of divided them between an optical characterization and quantification of what the optically active water components might be. And I think if you have a bit of lab experience, you will have done many of these measurements just for different reasons. Then one important thing to consider is that one trip to your field site is not likely going to be enough, because your water body looks a lot different between different seasons and perhaps when there's been a storm. So if you really want to start using remote sensing to characterize the whole surface layer of your water body, you will also have to repeatedly go to the field in the first place to find out what sort of optical variability is expressed in that water body. That's a lot of work. But then you can have some more confidence in your remote sensing products as well. So here's just one example. It's actually not from a lake, although you could call it a very big lake. It's from the Baltic Sea. It's relatively shallow, eutrophic, and has cyanobacteria blooms every year. You see that there's quite some difference in the expression of absorption between spring and summer peak growth periods, for example. And if we were to assume one standard shape, for example, in the K2RCC algorithm, for how this absorption translates to a chlorophyll concentration, it's not going to be the same between these two seasons. So an algorithm like K2RCC has actually been trained on this variability, on these possibilities. Another thing you need to consider is that water itself is not a constant absorption. It's fairly constant, but in the infrared, it actually has a temperature dependency. So unless you know it, that will cause some uncertainty. And you could do the same for the parts of algal particulates or detritus that isn't pigmented. You see, again, quite some variability. Okay, moving on. Another aspect to consider is when you go sampling, not just which day, but also the time of day. This is actually an example from an ocean area observed by a geostationary satellite. The advantage of geostationary is that they look at the same place all the time. So you just wait for the clouds to pass, get repeat observations. It usually doesn't exist for high latitudes, but around the tropics it can be very, very interesting. What you can see here is that some of the dynamics, hour on hour, actually change quite a lot. So this is a source of uncertainty, is all I'll say. And if we choose to believe what's in a remote sensing image, or if we choose to compare it to measurements made in the field, bear in mind, there's a time window involved in that analysis. And finally, I believe there's a spatial component to it. If you go to your lakeside and you take all your measurements from the shore, you're comparing a water column measurement that has actually the highest variability of your whole water body, because it changes a lot near the shore when there's a bit of wind, etc. And you're comparing that to the pixel in the satellite image where you have the highest uncertainty. So if you compare those two together, what you get is the worst case scenario. If you were to consistently go to the center of your lake, you're away from the influence of nearby land, which can mix its signal with that of the water. And then you normally get a more consistent response. There's just some examples here from the difference you observe in the reflectance when you are near shore. When you measure near shore with your satellite compared to what you have measured in the field. So what you have measured in the field is quite consistent between near shore and the middle of the lake. But what you see from the satellite might be rather different there. That's the final point. Hopefully that was quick enough. We can now go back. I don't know if we have 20 minutes. Somebody will tell me. But what we will do, and I will not start with the demonstration this time, because we will be able to find our way now. We are going to, first of all, get rid of the level 1 products that you had received. we're going to open the level 2 products, I advise that you just pick one of them, either the Ultra image, which has the advantage of more wavebands, more different products possible, but coarser resolution, or the Sentinel-2 image, which is higher resolution, pretty pictures, but the bands are quite broad, so we cannot say as much about what is in the water. And then included in those images, you will have some bands that have sort of this naming, which tell you what the membership is, the similarity to each of the optical water types that have been defined. So you can see that different pixels have different similarities to existing predefined water types. You can also skip that step. If you're looking at the Sentinel-2 product, you will have the results of individual algorithms for turbidity and chlorophyll A. So you can compare how different their outcomes might be. And if you go to either the Ultra or the MSI product, you will also have bands that look like blended turbidity or blended chlorophyll. And sometimes it's even using the top 3, 2, or 1 of the most similar water types. So there's a few different products to explore that give you some concentration estimates. So I would say, have a look around, observe what differences you see, and ask your trainer questions about what this means. And enjoy, and come back.
It's now 10 to the hour. So will we limit the amount of time we spend in this breakout room?
I would say 10 minutes is fine to have a look around. Yeah.
Okay, I'll change it to a 10-minute session then, if that's okay.
Thanks for a show.
Great, thanks Carmen, and thanks all. We'll make this fairly quick, but we wanted to start out by thanking all of you, the leaders, and especially Sophia and the GLEON Student Association. So Carmen, Igor, Stefan, Valerie, Alo, Johan, Mark, Nick. Thank you. This was a really informative workshop, and we appreciate your volunteering to run it and look forward to future activities. Paul, do you want to go to the next slide?
Sure. Oops. So yeah, and for me personally too, I learned so much. There was a lot of information. It was great to have the hands-on activities. Just a couple of words about GLEON. Some of you will be participating in the GLEON workshop that's happening next week. And a reminder that GLEON is the Global Lake Ecological Observatory Network, and we're really 3 networks. We're a network of people, data, and lake observatories. And we emphasize very much that we're a network of people. And we're built on a set of principles that really empowers and engages the community to participate in the science. And GLEON has a tremendous amount of resources, and the #1 resource that GLEON has are the people. And GLEON is also a learning organization. So we run a lot of experiments like what we're doing today with the remote sensing workshop. And I think this workshop is a really great example of how we can bring a community of people who have expertise in remote sensing together with a lake observatory community so that we can all learn and we can all grow together. And we appreciate that very much. And again, the principles of GLEON really are about sharing data and sharing ideas, and also building upon concepts of team science and collaboration so that we can all grow not only in the kind of resources that are available to all of us, but the science that we do together collectively.
Go ahead, Paul.
Oh, okay. I'll hit the first one if you don't mind hitting the second one, Kathy.
Okay.
So, looking ahead to next week's GLEON meeting, there are ways to get involved further in remote sensing activities. And Carmen has led the remote sensing ad hoc group for a couple of years now, and I think it's evolving pretty rapidly. On Friday, October 8th at 10 UTC, there will be a meeting of the ad hoc group. And I think if you want more information about that group, you could contact Carmen. Go ahead, Kathy.
Yeah, and the next GLEON activity that we're really excited to announce is that there will be an opportunity for early career scientists to gather together with some of our NASA colleagues to have another cohort of GLEON and remote sensing colleagues, again, early career, who will be focusing on the SPG mission, which is a mission that NASA is planning on launching a couple of years from now. So stay tuned for that opportunity. Again, international early career scientists to enter into a lake expedition and explore the possibilities of in situ data and remote sensing opportunities. And then there are some other opportunities as well that are kind of outside the purview of GLEON, but maybe something you want to avail yourselves of. One is Geo Aqua Watch, and here's the link for that. And the International Ocean Color Coordinating Group as well. Here's the link for that. And then further reading, and I noticed that many of the presenters referred to this further reading Mobley Ocean Optics webbook. So we would point you to those resources. And also, if I can, I would suggest that you might be in contact with the leaders of this workshop about further activities. One other comment is that there will be a survey that will be sent out to you by Valerie, I believe. If you could fill that survey out, that would be terrific. It's a survey that has been administered to other groups. And so it will be nice to have the GLEON workshop group respond to it. There it is, Stefan, thank you. And anything else, Carmen, any other comments from you?
Just thank all of the presenters and the trainers for being here, and it has been super long. I also want to thank all the people that went until the very end. I hope you learned something. I hope you are more interested now in remote sensing and using that for your studies. We are here for you. I mean, any doubt, concern, or whatever, you can always email us or contact to us through GLEON. And please join the other group if you are interested in remote sensing and aquatic remote sensing. So nothing. Thanks all, and hope you learned something. Have a nice day. All of you. Thank you.